Okay, good morning, everyone. I hope you can hear me clearly and can see the screen also clearly.
Yes, sir.
Okay, thank you very much, Mr. Kapil. Okay, so we had started on sensors, done the general thing as to what is a sensor. And remember, don't forget when you are giving the definition of what is pressure, then it is force per the force or pressure that is acting per unit area on a particular surface, but at right angles. Okay, don't forget that all important thing, at right angles. Okay, and we had seen the different pressure sensors. We had seen the differential pressure sensor. Okay, and today we are taking up this particular sensor, the piezoelectric pressure sensor. And remember, I said certain sensors are not practical for use on board the ship. This is one such sensor, the piezoelectric pressure sensor. Now, if you remember the piezoelectric effect, I think it was asked in one of the oral questions. It's a very common thing that we have learned years and years ago. Okay, whilst we were becoming electrical officers or we did some electrical course, we learned what is the piezoelectric effect. So what is the piezoelectric effect? If this gray section over here is the piezoelectric crystal, not every crystal, there are certain crystals. For example, you have some of them mentioned over here, gallium phosphate, tourmaline, and this is very commonly known to all of us. Okay, you find them in quartz watches. Okay, so one of those first watches that came out were quartz watches where you didn't require a battery to be put. Okay, so it had a crystal and that crystal is called quartz. Now, assuming that this is quartz over here, right? If this was quartz, let me just label it with a good color. Okay. Right? If this was a quartz crystal and it was sandwiched between two plates, conducting plates, and if pressure was enacted on the opposing sides of these plates, in other words, opposing surfaces of this quartz crystal, then it would develop a voltage. So let's see animation of this particular video. Okay. Okay, so you can see this is a very animated video in the sense it is showing you too much of compression. No crystal is going to get compressed so much, but what is it indicating? That every time you are going to be putting a pressure on the opposing faces of the crystal, a voltage is going to be developed. Okay, right. So that is what this particular thing is telling you about. Okay, so having seen that, we are going to put this very same principle into operation by making it a pressure sensor. Okay, we have seen, of course, you are not going to get huge voltage outputs, microvolts maximum, and therefore you'll have to amplify this particular thing, etc. Okay, now let us put that into perspective as far as this basic piezoelectric pressure sensor is concerned. So here you have the quartz crystal, for example. Okay, it can be any of those others, tourmaline or the other one also. So let's take it as quartz. Okay, so here's your piezoelectric crystal. It has been sandwiched between two conducting plates, and from these two conducting plates, you're taking your particular electrical connections to an output. Okay, an electrical circuit that is going to convert whenever pressure is acted, just like as we saw in that animated video. Whenever pressure is enacted, you're going to get a voltage output. So this voltage output is going to be directly proportional to the amount of pressure that is being enacted on this particular quartz crystal. Okay, and therefore that output, whatever the voltage is being developed and given at the output, that output will then be calibrated to give you that particular pressure. Let it be MPa, let it be bar, let it be kg per centimeter square, let it be even PSI. Okay. Now here, this particular crystal is sandwiched, as I said, between these two conducting plates. One of these conducting plates is fixed. And here's an insulating material so that the this conducting plate doesn't short anywhere else. There is an insulating material. And then when pressure is enacted in this direction, okay, it is as good as an equal and opposite pressure is enacted from the opposite direction. So that same principle is being followed, that when equal and opposite pressure is enacted on both these things, you are going to develop a voltage output proportional to this pressure that is enacting on the opposing phases. Okay, so where is this pressure being enacted? This is connected to a physical connector, this black section over here. Okay. And that physical connector is also connected to a diaphragm that is flexible. So the diaphragm, whenever there's going to be pressure enacted on the diaphragm is obviously going to be moving in the downward position, isn't it? From its normal position, it is going to go downward. And as it is going to go downward with respect to whatever force that is being enacted or pressure that is being enacted on this thing, obviously that pressure is going to come onto these two opposing faces of the quartz crystal and will develop a particular output voltage directly proportional to this pressure. Now also notice that it is acting at 90 degrees or at right angles or perpendicular to what? This surface area. Okay, so we are meeting all those requirements. Pressure, it is acting at 90 degrees to this surface area, and that surface area is getting deformed in the downward direction, whereby it is giving a force on this particular plate. But because this plate is fixed, you are going to have a corresponding force acting in the opposite direction. Okay, so we are meeting up with that particular piezoelectric effect, and therefore we are developing a voltage. This voltage will be directly proportional to the force that is acting on this particular diaphragm. And that is how your particular piezoelectric pressure sensor works. However, There is one drawback, and that's why I mentioned that it is not practical for use on board. Can anybody tell me the reason why? This is a very commonsensical answer to this question.
Due to vibration, sir.
Absolutely 100% correct. Okay, we are not on a ship that is having electrical propulsion. And generally we are going to be only on board ships that are having the diesel electric engine. Okay, the diesel electric engine at best of time gives us a lot of vibrations depending on where and how that ship is constructed. Even more so when the ship is running in ballast. Okay, there's so much of vibrations that even if a pressure is acting on this, those vibrations are going to make this particular diaphragm move up and down. Okay, so this is also going to be transferred to this piezoelectric crystal and therefore your output is also going to go up and down. Okay, so you're not going to get a proper pressure reading. Okay, if the pressure reading is going to keep on changing, what's the use? Okay, so therefore this particular pressure sensor called the piezoelectric type of pressure sensor is not practical for use on board. It can be used elsewhere where there is no vibrations at all. Okay, so that is the reason. Right, okay, so we've seen the piezoelectric crystal being used as a pressure sensor, and now let us see the LVDT. Linear variable, it is called the inductor pressure sensor or the LVDT. LVDT standing for linear variable differential transformer. Sometimes it's called the transducer, but we will retain the name transformer because it is using the transform. We did the transformer topic. So where you are having changing electromagnetic lines of force, you have a primary, you have a secondary, and voltage is induced from the primary into the secondary. So it is following the transformer principle, and the transformer principle works on whose laws? Faraday's laws of electromagnetic induction. Okay, so we will keep LVDT, T standing for the transformer. Okay, so what is this LVDT? An LVDT is an electromechanical device. Why electro? Because we're having or using this transformer. Okay, transforming or transferring your magnetic lines of force and therefore inducing voltage. So electromechanical. Why? Is because there is a core. Okay, there is a core that is physically displaced due to pressure. Okay, and based on this displacement of this core, you are going to get your voltages either more or less. So what is an LVDT? It is an electromechanical device that produces an electrical output that is linearly proportional to the displacement of this core, which can be moved up and down. Okay, so let us see now how this LVDT works. Okay, we will also see a video, but first let us see the explanation and how this LVDT works, and then the video will make things even clearer. Okay, so we talked about a transformer. So a transformer will have windings, primary windings. Okay, in this case, we are talking about a normal transformer having a primary and a separate secondary. Okay, in this case, your secondary is divided into two windings. We're not talking about an auto transformer. We're talking about two distinct windings, and here's your primary winding. Okay, and since we're talking about changing electromagnetic lines of force and Faraday's laws of electromagnetic induction, we will be giving a AC source to the primary. So you will be having a changing electromagnetic lines of force being emitted by your primary. Okay, we have a secondary. Now this secondary is divided into two equal parts. So the number of turns in this L1 of your secondary, the number of turns in your L2 of your secondary, as I said, is divided into two parts. Let's call it L1 and L2. Both the turns are the same, but L1 is wound in one direction. Let's assume it is in the clockwise direction. That same connection is taken and wound in L2 in the opposite direction, anti-clockwise direction. And then the output is taken across L1, L2. Okay. So here you will be having the current flowing in one direction here. And here in L2, you will be having the current flowing in the opposite direction. So L1 and L2 are wound in series opposition to each other. Note this. And why we have to note this is then we will come to know what will be the output depending on where this core is going to be moved. Right? So having understood that, now this core, when it is exactly in the center, it is linking L1 and L2 in equal proportion. Therefore, when an AC source is given to your primary, it will have electromagnetic lines of force. And remember, a core is used to concentrate the electromagnetic lines of force so that maximum voltage is induced in the secondary. That we have already seen in our transformer topic. Okay, so this soft piece of iron core is going to concentrate that electromagnetic lines of force so that an equal amount is induced in L1 as well as L2 when this particular core is right in the middle and intercepting both L1 and L2 equally. So therefore, the voltage induced in L1, let us call it as V1. Voltage induced in L2, let's call it V2. So the voltage induced V1 will be the same as the voltage induced in L2, that's V2. So V1 will be equal to V2, excepting that V2 will have an opposite polarity because it is wound in the opposite direction. Okay. So when, as we said, this particular core is exactly in the middle, let us see what is the output that we are getting. Let's say this was 10 volts. Let's change the color. Let's say this voltage was induced in V1 was plus 10 volts. Okay. Because this was wound in the opposite direction and having the same number of turns as your L1, excepting it is wound in the opposite direction, the voltage here was minus 10 volts. So what is your output voltage? The output voltage when this is exactly in the center, equally linking L1 and L2, that voltage VO, let's go a little down or put it over here, V out, okay, will be equal to V1 minus V2, okay, which will be 10 volts minus 10 volts. Therefore, your output voltage when this core is exactly in the middle is equal to 0 volts. So if you're going to draw the graph, when this particular core is right in the middle, you are having a 0 volt output. Okay. When this core is right in the middle, this is called the null position. Okay, and at the null position, your output VO is equal to 0 volts. Okay, now let us say there is some pressure acting, and actually this LVDT is used not only in your steering gear, but also your ME engines. Okay, I've got the name now. That day I was trying to find out what is the name of that B&W MAN engine, which is using this LVDT. Okay, so this is that B&W ME engine that is using this in a FIVA valve, FIVA, fuel injection valve adjustment or something to that effect it is called. Okay, those who have been on these ME engines will know exactly. It is not FIFA. Many say FIFA, and they're thinking of football rather than this type of valve. Okay, so oil pressure up to, I think, 200 bar, okay, maybe even greater. 200 bar, that's a tremendous pressure. Okay, so pressure of oil will be acting once in this direction and once in this direction. Therefore, when pressure of oil is going to be acting, okay, this is a hollow cylinder tube. When pressure of oil is going to act in this direction, obviously it is going to move this particular core towards the right. So let's say that it has moved completely to the right over here. Okay, and when it's going to move that much to the right, this part over here, and let me white it out so that you are not going to have this red part over here. Okay, right? So this core has moved in this direction and is now occupying almost quite a bit of your L2. It is not intersecting or intercepting L1 now. So what does the core do? It involves more voltage to be induced in L2 than in L1. Okay, so when it's acting in this direction, it's not going to be inducing any voltage in L1. It is going to induce maximum voltage in L2. And let's say, what is the voltage over here, just to make things easy? Okay, let's say now this is going to be 0 volts. Okay, and from here it's going to be 10 volts. Okay, and what did we say? Since it's in opposite direction, it's going to be minus 10 volts. So what will be the output voltage at this thing? V out, once again, V1 minus V2. Okay, V1, what did we say? No voltage is added because now this is gone that side. Okay, so this will be 0 volts minus 10 volts. Okay, so V out is minus 10 volts. And therefore, this is considered as the maximum direction that this core can move. So you can say it's 100% in this direction. And because we are getting V out as minus voltage, at 100% there, you're going to get minus 10 volts. Okay, when your core position has moved completely to the right, your voltage output is minus 10 volts. And that is your 100% where the core has moved towards the right. Okay, now let's take the opposite direction. If that particular pressure is going to be acting from this side, that oil pressure is going to be acting on this side, then what happens is this particular core is now going to move in this direction. So let me get rid of all this white portion here. Okay, okay, and now this, and now this core is now intercepting or interacting with this particular coil L1 and is no longer being interrupted or being interjected by coil L2. Okay, so I'm again going to put all the white over here as if your L1, your soft iron core is completely moved towards the left because of the oil pressure acting on it. So this coil, core is not intercepting L2. Therefore, you're going to get the reverse over here. Okay, so 0 volts over here. Let me make that red. Okay, so 0 volts over here. And this time you're going to get 10 volts over here. So what is the output? VO is equal to V1 minus V2. V1 is having 10 volts, V2 is 0 volts, your output is plus 10 volts for 100% motion of your particular core towards the left. And as you see over here, this will be plus 10 volts. So your particular core, depending on its position, will give either a positive output or a negative output or zero output. So negative, positive, or zero output. So wherever this core is going to be, anywhere in between, more this side, it will be more negative output, more this side, then more positive output. If it is right in the middle, as we saw at the start, then you're going to get 0 volt output. So based on where this is thing, that voltage is going to act, that is going to tell you where that particular thing core is going to be positioned. Okay. Everybody clear with your LVDT and its working? Any queries or doubts? Okay, so let's see a video on your LVDT and how it works. Okay.
Explain the construction and working of LVDT. LVDT is also known as Linear Variable Differential Transducer or Transformer. It is a passive transducer which measures displacement. It consists of a primary coil wounded on a hollow cylindrical rod and is connected to the AC source. It also consists of two secondary coils having equal number of turns and is wounded on a hollow cylinder at equal distance on either side of the primary coil. The two secondary coils are connected with each other in series opposition, so that the net induced EMF of the two secondary coils becomes, we see that a movable soft iron core is placed inside a hollow cylinder. Position of this core with respect to the two secondary coils will affect the magnetic coupling between the primary and two secondary coils. Let's now understand how this LVDT works. We see that when an AC source is activated, alternating current starts flowing through the coil, due to which varying magnetic field is produced. Now when this varying magnetic field interacts with the secondary coil, an EMF is induced in the two secondary coils. We see that initially the core is placed in such a position that equal EMF gets induced in both the coils, due to which the net EMF of the two secondary coils becomes zero. This position of the core is known as null position. Now if we move the core towards the right, we see that the flux linking with coil S2 becomes greater than the flux linking with coil S1. As a result, the EMF induced in the coil S2 becomes greater than the EMF induced in coil S1, and the net EMF shows a negative value. Similarly, if we move the core towards the left, we see that the flux linking with coil S1 becomes greater than the flux linking with coil S2. As a result, EMF induced in coil S1 becomes greater than the EMF induced in coil S2, and the net EMF shows a positive value. Thus, LVDT uses the magnitude and polarity of the net EMF induced to measure the displacement of its core from the null position.
Okay, so now everybody's clear with how your LVDT works. In other words, your inductive type of pressure sensor. Okay. Okay, so as usual, whenever I finish a certain topic at the end of the class, I post it to the institute and they upload the thing on the app. Videos will not be uploaded because they are already being recorded in the lecture. Okay. So you can always go back, select the lecture, and then go through the videos in case you have any doubts. Okay. So before we move on to the next type of sensor, which is the proximity sensor, any queries or doubts you have on the pressure sensors that we discussed? Right. So let us move. Somebody has any doubt? Yeah, go ahead.
Sir, can I know where we are using this LVDT except steering gear and you said main engine BMW? Where?
In your main engine, it is used, as I said, as a FIVA valve, where that
Okay.
like that particular thing, one side when the core is going to be moved, it is going to inject that much of fuel into the unit of the main engine. Okay.
Okay.
If it is at an intermediate position, then it's going to inject only that much amount of fuel. If it is completely to the right hand side, it's going to inject much more fuel. If it is towards zero, then it is going to, when it's going towards the center position, that is the null position, it is going to inject less and less fuel. So when you're going to inject more fuel or less fuel, obviously the amount of exhaust gas has to be exhausted from that unit. So when it is going to move in the other direction, then accordingly that exhaust gas valve will be open at the appropriate position. It doesn't have to be open fully. So whatever that exhaust gas is then available will then be exhausted when the soft iron core is moved in the opposite direction. So that is why you get very, very precise control for an ME engine. You can go down even up to 2 or 3 RPM. It is so controllable, unlike your normal diesel electric engine, where if it goes below a certain RPM, then your main engine comes to a stop. Okay, not so with this ME engine. It is very, very easy to control, going down even to a very, very minimum RPM. Okay, in the steering gear, since I'm not taking any steering gear things with you, I think Mobin sir is doing that. It would be better to ask him about where it is used, but where I can think it is used is with regard to opening and closing of your solenoid valve, so that when you're giving a command, your solenoid valve, either if you're giving it to the starboard side, it will move to the starboard side. If you're giving it to the port side, then your rudder will be moving to the port side. So just using common sense, I think that is the way it would work. But to give you an exact operation of the LVDT for your steering gear, possibly Mobin sir would be able to give you a much better answer for that. Okay.
Okay, sir. Thank you.
You're welcome. Okay, so let's now move on to another topic, and that particular topic is proximity sensor. What is the meaning of proximity? Proximity means nearby, in the presence of a nearby object. So just to give you a very rough idea, going out of the electrical circuit, and since we are still not out of the pandemic, let me use the pandemic thing of proximity. Okay. This guy here in red has got the COVID. This is you. Both are not wearing masks. Okay. Both are not wearing masks, and you pass by him, and at that particular time he gives a God Almighty big sneeze. Okay, maybe less than 3 feet, and you've carried on walking, and he's gone in the other direction walking, and then one day you find You have a headache, you have fever, your body is aching, and you have now got COVID. Okay. You didn't touch him, he didn't touch you, but still you got COVID. How? Because you were in close proximity to this guy when he sneezed. He didn't know he had COVID. Okay, so he said, "Arey, my nose is suddenly started." He gave a nice sneeze, and then you got it without him touching you or you touching him. That is the meaning of proximity, nearby. Okay, you were nearby him, you were in the close proximity of this guy, and therefore you got the COVID because he sneezed. And the germs were transferred to you in that sneeze. Okay, so that is the meaning of proximity. Now, proximity in the terms of sensors is meaning one and the same thing. A sensor is going to detect an object without touching that object. Only when that object comes in closeness, nearby, or in proximity with that sensor. Okay, so now these sensors will be of different types. They will be electromagnetic type, they will be capacitive type, they will be with regard to on-off, beam on, beam off, okay, or even by means of a transducer such as sound, okay, and we will see each one of them, how they are going to be working, okay. So the common types, when we are talking about an electromagnetic type or inductive type, that will be working of this electromagnetic principle. Capacitive type, once again, C is equal to epsilon multiplied by A divided by D, all that comes into play. Okay. Photoelectric type, which is beam on, beam off. And the ultrasonic, when they are talking about sonic, it means something to do with sound. Okay. So let us take all these four, because we have all these four on board our ships. Okay. Let's take the first one, the inductive type of proximity sensor. Right, first and foremost, we have this very commonly in our engine room. I'm not talking about elsewhere on the ship. You can have it in many places on board the ship. Just let's take the engine room only. Where can you find an inductive proximity sensor? We'll see how the working and all that is. Where in the engine room can one find an inductive proximity sensor? Anybody? Come on, guys.
RPM indicator,
Yes, RPM for
main engine flywheel,
main engine, then
Generator.
huh? Two guys spoke at the same time, so I couldn't make out. Any one of you answer?
Generator RPM.
Yes, generator RPM, because you're having this thing over there for your generator, by your generator flywheel. Then
Purifiers,
yes. One more, at least one more.
main engine turbocharger, sir.
Yes, absolutely right. Okay. So these are the four places where you can find this particular type of proximity sensor. Main engine flywheel for your RPM detector, your main engine turbochargers to pick up the RPM. That is why you're getting that RPM displayed in your ECR, on your ECR control console. Your purifiers at the horizontal shaft, because it has to detect the speed of the purifier when the bowl opens. That is why when the bowl is supposed to be open to desludge, it actually, the water is injected and lifts the bowl, and because it lifts the bowl, your RPM is supposed to drop. Okay, so you're having this particular sensor to detect that particular speed dropping. And it is then being fed into a circuit whereby if that speed is not detected as dropping, then it will issue an alarm. And what is that alarm that you get for your purifier? Bowl no open alarm, okay, or no discharge alarm. Okay, so that's where it is used. And the fourth place is your auxiliary engines by your generator flywheel, okay, because you are having an RPM sensor over there to detect that the RPM is of a sufficient distance. Okay, right. So we have seen in the engine room, it can be used elsewhere also, plenty of places. Instead of having limit switches for your engine room crane, you can have it there as well. Okay, you can have it for your roll on, roll off, where those doors at the bow as well as the ramp, okay, if it is a passenger vessel, that is why some years and years ago, there was a P&O vessel which was transiting between France, Calais and UK, which is Dover, and it capsized, and then nobody knew why it capsized suddenly. Many people lost their lives. They later on, after this thing, they found that the bow door was not fully shut. And deeper investigations, they found that one of those sensors that was to detect that the bow was fully shut was malfunctioning. Okay. And then when the ship picked up, that ferry picked up speed, it started taking in water, and the ship got flooded and then lost its stability and capsized. Okay, so you can have it in various places, but we have seen where it can be used in the engine room and the four pertinent places where it is used in the engine. So how does this proximity sensor work? Since we are talking about inductive, then again we are talking about electromagnetic lines of force. You are having an inductive coil over here right at the front end of this particular sensor. And this inductive coil is connected to an oscillator. So when there is an oscillator, you're always talking about something that is going to be varying at a certain frequency. So that is going to be pumping a current, and that current is going to make a particular electromagnetic field, which is going to be varying as per the oscillations of this oscillator. So here you're getting a changing electromagnetic field, and therefore your Faraday's laws of electromagnetic induction come into play over here. Okay, so here you have this oscillator. Here is what you have as the Schmidt trigger. And finally, you have an amplifier. And of course, what is not shown here, you have a relay. And then that relay is going to switch on and switch off. And therefore, what are you going to get? You're going to get a square wave output, meaning either a 0, which is here, or a 1, which is here. Okay, so you're getting a proper 0 or proper 1 depending on your relay on or relay off. Okay, so first and foremost, okay, we've seen what the oscillator is doing. It is giving a changing electromagnetic field over here. Well, the current over here is always changing depending on the frequency of this oscillator. What is this Schmidt trigger doing? The Schmidt trigger is going to be detecting, okay, you have this oscillator that is giving a cycle, an AC cycle. On this AC cycle, you might have a spike going up or you might have a spike going down. Okay, and if you are going to have a particular thing where the cut-in is going to take place, okay, and a cutout is going to take place, therefore you will be getting a proper square wave like this, which is then going to be amplified and drive that relay on and off. But if you're going to get a spike, then okay, maybe it will cut on at that particular thing, but when it's going to get a spike downwards, it might think that the voltage is dipped over here and it will cut it off. So instead of getting this square wave, you're going to get this square wave. And then it's returned back to the normal, and therefore it is going to come up over here, and then finally it is going to come down at this particular junction, and then so on and so forth. Instead of getting 2 square waves, you might be getting any number of square waves over here. And if that particular square wave, okay, remember the RPM of the generator, the RPM of your particular main engine, and especially your main engine, all that goes into your safety circuits of your main engine to control certain things of your main engine, such as your fuel injection, such as your lubrication of your main engine unit. If this is going to be detected, okay, this type of square wave is going to be detected instead of this square wave, then your whole thing is going to go out of sync with regard to your main engine, and your main engine can probably fail very, very badly. Okay. Therefore, this Schmidt trigger is going to detect a distinct on and a distinct off section of this particular frequency whenever some object is detected. Okay, so that you do not get any spurious square waves like this. Okay, you want a proper square wave, okay, at a particular regular interval, rather than something caused by noise. So basically, your Schmidt trigger is going to knock off those extra noises by adding a particular cut-in threshold and a particular cutout threshold. So before going further, let us see what the Schmidt trigger is doing. Schmidt trigger is doing a very small thing by giving a cut-in threshold and a cutout threshold. We'll see a full, not a full video. We'll see only part of that video, which is showing you this particular thing of your Schmidt trigger and how it works. Okay, so let's see the Schmidt trigger.
Hello, Dan Nedelkowski here from howtomechatronics.com. In this tutorial, we will learn what is Schmidt trigger and how it works. The Schmidt trigger is a logic input type that provides hysteresis or two different threshold voltage levels.
Okay, so here they have shown a very noisy signal. Okay, when we are going to see the video on the inductive proximity sensor, I will draw your attention to the particular sine wave. That means your oscillation sine wave. And then before showing you that thing, as the video is going to be shown, you will have to pay note to those spikes that are there. Okay, here they have shown a particularly noisy wave and how this Schmidt trigger is going to neglect this particular dip which is there. Okay, we'll see it a little later in this video, and I will pause the video at that particular juncture because that's all we need to see with regard to this Schmidt trigger.
For rising and falling edge. This is useful because it can avoid the errors when we have a noisy input signals from which we want to get square wave signals. So for example, if we have a noisy input signal like this that is meant to have two pulses, a device that has only one set point or threshold could get incorrect input and it could register more than two pulses as shown in this illustration. And if we use the Schmidt trigger for the same input signal, we will get a correct input of two pulses because of the two different thresholds.
Okay, so up to here I'll be showing the Schmidt trigger because we don't need to show the rest. You can see what this noisy signal has done. If there was only one threshold, it will only cut in at that threshold, and then because of this dip, it's gone below that threshold, and therefore you're going to get one particular pulse, square wave. And then again it's gone beyond this threshold, so it's again going to cut in, and then again it's come below that threshold, so you're going to get another pulse. Okay, likewise here also, it has come above over here, and then it's gone below at this particular junction, and then again it's gone above over here. So you can see not only are you getting false pulses, the width of those pulses are also incorrect. Okay, so you can see if this is going to be fed into a main engine safety system, what havoc is going to cause. Okay, whereas when you're going to introduce this Schmidt trigger, which is nothing but a threshold detector, you have distinct cut-in and cut-out points. So only when it goes above this cut-in point will it go from 0 to a logic 1. And only when it comes below this threshold value, the lower threshold value, then only it's going to cut off. So you get proper and same width of your square waves, okay? And then this is what is going to be fed into your safety circuits with regard to your main engine, or even for that matter, your generator engine, okay? So everybody's clear with what is your Schmidt trigger and how it works? Right? So, of course, these square waves are going to be very small, so therefore they'll have to be amplified. When they're amplified, then they're given to a relay which switches on or switches off, and then that signal is sent down to, for example, your main engine safety circuit, etc., for the controlling of your main engine. Okay, now let us see how it works. We said an inductive proximity sensor, and using Faraday's laws of electromagnetic induction, how does this sensor work? As I said, your oscillations are going to be giving an changing electromagnetic lines of force the moment the power supply is given, and the power supply that is given is between 10 to 30 volts DC. Okay, 10 to 30 volts DC. Okay, that is the working voltage of these proximity sensors generally. When that voltage is applied, anything between 10 and 30 volts DC, your particular oscillator starts to oscillate. It is oscillating and producing this electromagnetic lines of force, okay, as shown, acting in this direction. And this sensor is going to detect an object if that object is going to come and cut these electromagnetic lines of force. Now, which object? Not any and every object, only metal objects. Okay? Only metal objects. If it comes and cuts these lines of force, then only this inductive proximity sensor is going to work. Okay, so now this is acting as your primary, and this metal object is acting as your secondary. So when the electromagnetic lines of force are going to cut a metal object, such as copper, iron, and so on and so forth, even aluminium. Okay, if that is brought over here and these electromagnetic lines of force are going to cut that particular metal object, then voltage is induced into this object. Remember when we spoke about the iron core of your transformers? Voltage is induced in that particular iron core, and then you will have currents flowing in that iron core. The currents flowing in the iron core for your transformers was called eddy currents. Likewise, here also the voltage that is induced in this metal will be having currents flowing, and that is also called as eddy currents. Eddy currents are in a circular motion. Okay, that is why it's called eddy. It is running in a circular motion, and they were going to be producing their own electromagnetic field of electromagnetic lines of force. Okay, and as you can see from this particular diagram, this particular figure, the field that is produced by these eddy currents that are shown in green, those electromagnetic lines of force are acting in the upward direction. Original electromagnetic lines of force are acting in the downward direction. So one in the downward, one in the upward. So the electromagnetic lines of force are going to start cancelling out each other. When they cancel out each other, it is going to load onto this oscillator to make the oscillators stop oscillating. So when this metal object is going to go out of the field, your oscillator will start oscillating. When that metal object comes within that field, your oscillator is going to stop oscillating. And therefore, your Schmidt trigger is determining when it is going to cut in and when it is going to cut out. So you will be getting the proper square wave output. Of course, you're going to get it very small. So that particular waveform will then be amplified. Once it's amplified, it is sent to an on-off relay. That relay is going to give you this much magnified square wave output. And then it is fed onwards to whatever circuitry that this particular inductive proximity sensor is connected to. Okay, everybody clear how your inductive proximity sensor works? Any queries or doubts? Right, so let us see in a video how this inductive proximity sensor works. And once again, I would like to draw your attention that once you see the oscillations, is going to connect it to an oscilloscope to show the oscillations. Your oscillator is oscillating. And when that thing is being generated, yes, it's picking up some noise. As I said, you have spikes going up and spikes going down. Okay, so let's see this video, the inductive.
Okay, today in this video, we're going to look at...
One second.
Okay, today in this video, we're going to look at proximity sensors. Now the device you see here is an inductive proximity sensor, so it will detect ferrous and non-ferrous targets. The power input to this module is 10 to 30 volts DC, and this is the sensor face, and all electronics is housed in this watertight cylinder enclosure. The exterior of the enclosure is threaded, so when you mount it in a bracket, you can actually fine-tune the operating distance. Now on the back, you can see two status LEDs. One indicates power, and the other one indicates the switching state. So when the target is within the operating distance, the detection zone, that LED will come on and a relay inside the enclosure will activate. Now the operating distance of this particular sensor is about 10 millimeters. So when you have a target within 10 millimeters of the sensor face, the status LED will come on and the relay will be activated inside the enclosure. So next we'll power this device up and we'll check out its operation. Okay, the sensor is powered up and you can see the status power LED is on. And I'll bring a ferrous target up to the face of the sensor, and when it gets within the detection zone, you'll see the status LED come on, as you see there. And every time the LED comes on, it's activating a relay inside the enclosure. And next I'll use a non-ferrous target, so I'll use an aluminum plate. And you can see there it's detecting an aluminum plate. I could also use a copper-clad PC board, so it would be copper, and it's also detecting that. So inside this sensor, there's an LC oscillator, and the coil is mounted close to the face of the sensor, and the oscillator is running at about 200 kilohertz. Now it's putting out electromagnetic field from the face of the sensor, and when a target comes within that magnetic field, it generates eddy currents in the target, and it actually absorbs some of the energy from the oscillator, and it loads down the field. Now the sensor inside detects that, and when it loads it down far enough, it actually will trigger a threshold detector and trigger the LED and activate the relay. Okay, to check out the internal workings of this proximity sensor, I have built this little pickup coil. It's just some hookup wire wound in a coil and hooked up to my scope probes. And what I'll do, I'll put the pickup coil around the sensor, close to the internal coil of the sensor, and I'll be able to pick up the oscillator, the internal oscillator of the sensor, which is creating the magnetic field. And then when I bring a ferrous object close to the sensor, we'll see it will cause the output to drop, which will trigger the sensor. So we'll hook this up to my scope, and we'll actually see this in operation.
Okay, now he's going to connect it to his oscilloscope, and it'll be showing an AC sine wave. But note, on that AC sine waves, there are spikes going up and the spikes going down. Okay, that's enough to give false square waves. Okay, if there was no threshold detector in the form of a Schmidt trigger. So the moment he shows AC sine wave, just notice the spikes going up and down. Okay.
Okay, the pickup coil, which is hooked up to my
You can see
scope
the
probes,
spikes,
is placed over top the proximity sensor, as we can see
especially
here.
on the positive.
And you can
going
see on the
wave.
scope it's picking up the internal oscillation, which is about around 200 kilohertz. Now this is a changing magnetic field, so when I bring a ferrous object into the field, it will generate eddy currents into the target, according to Faraday's law of induction. And when the eddy currents are induced into the target, it'll actually load down the field, and you'll see the scope amplitude will drop, indicating it's being loaded. And when the sensor senses that, it'll actually trigger the output. So as I bring the ferrous target close to the sensor, you can see it's loading down the field. And after it loads it down, the sensor will activate its internal relay. Okay, so now you have a good idea of how a proximity sensor works.
Okay, so that's how your inductive proximity sensor works. Okay. Everybody clear? Any queries or doubts on how it works? Remember, your inductive proximity sensor will be able to detect metal only. Okay. You bring your hand, you bring a wooden piece, you bring plastic. No, it's not going to detect it. It is working on the principle of electromagnetic induction governed by Faraday's laws of electromagnetic induction. And that's how, as you saw, your inductive proximity sensor works. Okay. Right. So that was the inductive proximity sensor. Let us see your capacitive proximity sensor. Now, your capacitive proximity sensor has the very same internals of your inductive proximity sensor, excepting that this time, instead of coil, you are having a plate or the plates of a capacitor. No more are you having an inductive coil, you are having a plate or a capacitor over there, having two plates and a dielectric. The dielectric is nothing but air. Okay? Air inside, air outside, one and the same thing. And we are having that all too familiar formula, epsilon multiplied by A divided by D gives you the capacitance. Any one of these parameters changes, your capacitance either increases or decreases. This capacitance will then be given to an electronic circuit that will be once again giving you a square waveform, which can then go to the various circuits in order to give you that particular control for that particular equipment. Okay, so let's see this particular capacitance type of proximity sensor. Okay. We are having air inside and outside, and everybody knows what is the particular dielectric strength of air. Dielectric strength of air, epsilon, okay, is equal to 1. If there is something other than air, let me say it is a piece of wooden block, then epsilon will be something greater than 1. For each particular material, epsilon will be changing from 1 to something greater than 1. If you're going to have your hand over there, that is changing it from air to your hand, which will be having its own dielectric strength, which will be greater than 1. So depending on what is the object that is going to come and cut these field lines, capacitive field lines, then your particular sensor, the capacitive sensor, is going to detect that object. Any object, okay, any target, any object, because we are changing it from air to something greater than 1, which means whatever the object that is changing this epsilon, you are going to get this particular object detected. Okay? So, what is going to happen? When that particular voltage is given, same 10 to 30 volts DC, as we had for our inductive proximity sensor, the moment the voltage is induced, your oscillator, in the case of your capacitive proximity sensor, your particular oscillator is not going to start to oscillate. Whereas in the inductive proximity sensor, what happened is when we gave that voltage, your oscillator started to oscillate. In the capacitive type of proximity sensor, when that 10 to 30 volts DC is provided, your oscillator does not start to oscillate. However, if you bring a target in to intercept these capacitive lines of force, that is going to be changing your particular epsilon to something greater than 1. And therefore, as C is equal to epsilon multiplied by A divided by D, since epsilon has changed and gone greater than 1, capacitance has changed, that is going to kick your particular oscillator into life. So your oscillator will start to oscillate. Your Schmidt trigger is going to determine the particular cut-in and cut-out points, and your amplifier is going to amplify it, and you're then going to get that proper square wave output. Okay? So in the case of a capacitive type of proximity sensor, your oscillator starts to oscillate only upon detection of an object. Whereas in the inductive proximity sensor, when that object was detected, then the oscillations stopped. Okay? And based on this particular principle, your capacitive proximity sensor works. By the way, the capacitor that is used in this, since it is using air, the same air that is outside, this type of capacitor is called an open capacitor. Okay? No other dielectric is used. The dielectric that is used is the same air that is outside of that particular proximity sensor. Okay? Everybody clear? With regard to your proximity sensor, the capacitive type of proximity sensor. Remember, the capacitive type of proximity sensor can detect any object, including metal objects. Okay? Let us see a video on how this capacitive proximity sensor works.
Welcome to GTV. Today I will be showing you what a capacitive proximity sensor is. Capacitive prox sensors can be used to sense both metallic and non-metallic material. Some ideal applications include liquid level detection, material level control, counting, and induction molding processes such as the detection level of plastic pellets in a feed hopper. A capacitor consists of two metal plates separated by an insulator called a dielectric. Capacitive proximity sensors can detect any target that has a dielectric constant greater than air. The dielectric constant is an electrostatic field generated by the oscillator circuit. If an object enters this field and causes interference, oscillation then begins. The detector or trigger circuit monitors the oscillator's output. When it detects sufficient change in the field, it switches on the output circuit. The output circuit remains active until the target is removed from the sensing field. Sensing ranges can depend on the material needed to be detected. There is no derating factor to be applied when sensing metal targets, but other materials do affect the sensing range. Sensors can be used to detect liquid through a non-metallic material such as glass or plastic, but they need to be mounted so that the sensor detects just the liquid and not the container. Generally, the sensing distance for capacitive prox sensors is greater for larger or denser targets, but the effect on the electrostatic field produced by non-conductive material can be quite small. Usually, sensing distances with this material is short. Materials such as ungrounded conductive material can be sensed from further away because it causes more interference on the electrostatic field. Grounded conductive material causes even more interference and thus has the longest sensing distance. Since the composition of the material and ambient conditions can have an impact on the sensing field, many capacitive prox sensors are equipped with sensitivity adjustment potentiometers. Capacitive prox switches can detect material at greater ranges from inductive sensors and have a long operation life. Capacitive proximity sensors, along with thousands of other products and services, are available at gelco.com.
So that was your inductive and capacitive proximity sensors respectively. Any queries or doubts on the operation of both these particular proximity sensors? Right. So let us see the differences, the basic differences between your inductive and capacitive proximity sensors. In the inductive proximity sensor, when a voltage is supplied to that sensor, your inductive proximity sensor oscillator starts to oscillate. On the contrary, your capacitive type of proximity sensor, when power supply is given, the oscillator remains off. It does not start to oscillate. In your inductive proximity sensor, when an object is detected, then the oscillator stops oscillating. In comparison, your capacitive proximity sensor, when an object is detected, then the oscillator starts to oscillate. And in inductive type of proximity sensor, what is the object that can be detected? We saw, because we are talking about electromagnetic lines of force, only metal objects can be detected. In comparison, capacitive proximity sensor, because we are talking about electrostatic lines of force, there is a difference between electrostatic lines of force and electromagnetic lines of force. Because electrostatic lines of force are going to be cut, then your particular oscillator starts to oscillate. Because epsilon has changed from 1, the dielectric strength has changed from 1 to something greater than 1, changing the capacitance, which then kicks that particular oscillator into life. Okay? These are the basic differences between your inductive and capacitive type of proximity sensor. Right, let us go now to the photoelectric proximity sensor, which deals with beam on, beam off. Okay, and to give you two very pertinent examples with regards to sensors on board the ship that is acting on, beam off principle. One very good example is none other than your OMD, oil mist detector. Another good example is your smoke detector that is using light to detect whether smoke has come or it is detected smoke or not. When we will be doing the fire detection sensors in the form of smoke detectors, we will be discussing this particular one where it is working on, beam off principle. But let's take this very first one, the OMD, oil mist detector, and how it works based on the beam on, beam off principle of this photoelectric sensor. In your particular OMD, there are two absolutely distinct types of OMD. One is the direct type, as shown on the left-hand side, okay, whereby you are having a light transmitting source, and that light is sent out in a particular tube, so that light is going to go straight across that tube, and at the end of that sampling tube, you're going to have a light receiving detector. In this case, the photodiode. Okay. So when the light is going to be falling on this particular photoelectrode, you will be having a current that is going to be flowing because the light is falling on this, the resistance falls, and a current is then going to flow. So basically, that is given to your alarm circuit as a beam on. So this will be a logic one. And if then you are going to have smoke, okay, so let's say that smoke is coming over here. And in this case, when you're talking about the OMD, that is oil mist is coming, that oil mist is going to obstruct the light that is falling on this. So therefore, from a logic one, what is going to happen? Current was flowing because the resistance has decreased. Now suddenly the resistance has increased. And the current is now going to stop flowing through this particular element. And that to the alarm signal is that your particular logic one has now fallen to a logic 0. And that particular fall from 1 to 0 is a trigger to your alarm circuit, and thus your alarm is given for your direct type of OMD. You also have an indirect type of oil mist detector these days on board ship, in the form of having your main unit inside your ECR. Okay, so this is your main unit. Let's change that. Okay, this is your main unit. And this particular main unit is located within the ECR. This one is located on the side of your main engine. Okay, whereas this particular thing, the main unit I'm talking about, is located within the ECR. And on each unit of your main engine, you will be having something that looks like this, with a probe. So if you're going to have your main engine like this, okay, I'm just showing only the bottom section with all your unit doors, scavenge doors. Okay, you will be having this particular thing located just outside over here. Okay, for each of those main engine units. And of course, when you're going to have for the end where the chain is over there, then you're going to have that particular unit also outside where the chain section is of your main engine. Okay, so outside each of your main engine units plus the chain unit of your main engine. Okay, This one will be having a probe that is extending into the main engine near all your shaft bearings. Okay, you are having your piston moving up and down and converting a vertical movement into a rotational movement. So that particular space can get or develop oil mist. That is why these sections are kept over there. So these sections, called a transceiver section, is sending out a UV beam, okay, across that particular unit that is reflecting off a reflector and coming back. Some of them are of this type. Some of them suck in that particular atmosphere within the unit and you have the beam within it. Okay, so that beam can be interrupted by none other than your oil mist, as you had in this particular case of your director. Okay, so whether it is being transmitted across to a reflector and back, or whether it is being sucked into this particular unit, you are having that light in that small chamber that this particular thing is being sucked into. That is going to have a particular transmitting light and a receiver, something similar to this one, inside of this unit. Okay, and therefore what is going to happen if that beam is interrupted? Then you're not going to get any output over here from this transceiver. And that output, if it's not going to be got by your main unit, remember they are communicating with each other. Okay. If that main unit is not sensing that the light has been detected, what is it going to do? It is going to raise the alarm. So based on the beam on, beam off principle, that your particular photoelectric sensor is going to be working. Okay, everybody clear? Any queries or doubts? Now, of course, this type, the indirect type, have LEDs indicating. Okay, when we did PLCs, what did we see? That your PLC, some of them have this type of combination, green, orange, and red LEDs, right? And what did I say? If the green LED only is lit, generally the other two are off. That means everything is working properly. However, if the green and the orange LED is lit with the red one off, that means the orange is telling you that there is some temporary error. And that is going to send an alarm to your main unit. Your main unit is going to see there is no particular communication between these two. Okay, so it could be a temporary glitch if the communication is broken. In other words, like a hang-up of your computer or your laptop, etc. Similarly, this is also a mini computer. So it is hung up and is not communicating between both these. Then you switch on and switch off the unit. And you'll find 99% of the time, this particular orange LED will be thing. If the communication is totally lost for whatever reason, then of course, this particular unit will have to be changed, despite you switching on and switching off. Okay, every time if this is there, then it's an indication that this transceiver unit has gone coupled. Okay, but if the green LED, remember the green LED is indicating power supplied normally and everything is working okay if these two lights are not lit. But if the green and red LED are lit, that means something has fatally gone wrong again with this. Okay, and in which case you'll have to replace this unit and also address, because this is communicating with each other. If the wrong address is given, then it may not read this particular thing and it will show an error on your main engine unit. Okay, so this is how your photoelectric proximity sensor works. Okay, guys, just give me a moment or two. Okay, so finally, the last type of proximity sensor, and that is your ultrasonic type of proximity sensor. Now, your ultrasonic type of proximity sensor works on the principle of sound transmission and reception. Okay, it can be compared to your radar where your RF signal is transmitted and received back. And therefore, you can detect your particular targets. In the case of the ultrasonic type of proximity sensor, this particular thing is none other than a particular echo sounder on board our ship. Okay, so we are having our ship, and generally the echo sounder sensor or transducer, as it is called. Remember, a sensor is a transducer, but not all transducers are sensors. Okay, right. So here's the hull of your ship. Okay, and this particular transducer, your ultrasonic transducer, is normally located right forward of the ship. And then it is going to be transmitting a sound wave that is going to hit the particular seabed. So this is your seabed. Let's color it brown. Okay. It is going to hit the seabed, and then it is going to come as an echo up to the transducer. And then, of course, is going to convert. Basically, a transducer is one that converts one form of energy to another form of energy. So in this transducer, what is going to be given is a tremendous amount of voltage. So voltage is given, and then it is going to be transmitted in the form of sound energy. So sound is going to be transmitted and then comes back to the thing as sound. And then it is going to convert it back into a signal that is of voltage. So one form of energy being converted into another form of energy, and then it's going to be sent to your main unit on the bridge in order to indicate what is the depth between your ship's hull and the seabed. Okay. So based on this, in the sense that we are going to be using that same particular formula that we used in the radar, where D, in other words here, the depth, is equal to T multiplied by SO divided by 2. In the case of the radar, this was speed of light, okay, which was also equal the speed of your RF energy that was transmitted by your radar signal. And in the radar signal, we were taking as 300,000 kilometers per second as the speed of light or of this RF energy, or because we are using that as a nautical radar, we were taking that particular figure as so many nautical miles per second as the speed of light or the speed of that RF energy that was transmitted. In the case of this particular echo sounder, we are talking about sound. Okay. And because we are talking about sound, sound travels at this particular speed in air, but in seawater, it is having this type of speed. So in water, sound travels much, much faster than in air. That is why whenever they are going to be tracking whales and all that in the sea, because they are always transmitting and communicating with each other by means of the sound, they are able to track it because that sound is going to be traveling much faster, and they'll know, okay, this whale is over there and this is the way they are going to be proceeding, etc., etc. Okay, So 1,500 meters per second in air as compared with 343 meters per second in, sorry, this is 1,500 meters per second in water as compared to 343 meters per second in air. Okay, so that's how this type of proximity sensor works. Okay, so everybody clear with the proximity sensors? Any queries or doubts on any of these 4 proximity sensors that we discussed? The inductive proximity sensor, the capacitive type of proximity sensor, the light or beam on beam off proximity sensor, okay, and then the ultrasonic sensor, which is working on the principle of sound transmission and reception. Okay, so having seen that, let us now see some more sensors, and that will be your temperature sensors. Just give me a moment. I'll have to bring that up. Okay, so your temperature sensors. Now, once again, temperature sensors with respect to what we use on board only. Okay, they are not, you are going to be appearing for an exam that is marine related, and then you're going to be joining the ship. Okay, so questions will be asked with regard to what type of temperature sensors can you find on board ship. So your answer to that question will be thermocouple, RTD, and thermistor. Don't say thermocouple, PT100 and thermistor. PT100 is a type of RTD, and we will see that shortly. What is PT100, what is PT500, and so on and so forth. But your correct answer will be thermocouple, RTD, and thermistor. Your thermocouple, as we saw right in the beginning when we started off the topic on sensors, we saw that a thermocouple is an active device, meaning that it generates its own power and works based on the power that is generated by it. Okay. Right. So what are the types? First and foremost, on what principle can it be called an active device, and on what principle does it generate its own power? Everybody knows this because we have done this whenever we had first started all our electrical courses and all that in order to study about electricity. And we know that a thermocouple works on the principle of Seebeck effect. What is Seebeck effect? Seebeck effect is that when there are two different metals, and let's indicate these two different metals by two different colors. Okay, when two different metals are joined together at a particular junction, okay, let's indicate the join by a different color. When two different metals are joined together at a junction and then you heat up this junction, okay, you're going to heat up this junction. Then if you're going to take a voltmeter and connect it over here, this is going to show you some voltage. What is this voltage that is developed? The voltage that is developed over here between these two connections is going to be directly responsible due to this heat. So it is directly proportional to the heat that is being put at this particular junction. Okay? A potential difference is created based directly on the amount of heat that is heating up this junction. So therefore, you will be getting whatever this voltage converted and giving you a temperature output. Okay, whether it's degrees Fahrenheit or degrees centigrade, okay, that will be calibrated to give you a particular reading. Okay. This voltage that is output over here is not a thing in volts. It is nanovolts, millivolts, max to max, microvolts. Okay, maximum. Okay, so if you're going to get such a small voltage, then obviously it has to go through an amplifier and then given to the circuits. By the way, before we go on with regard to this, I forgot to show you a video. And that video is with regard to how you would detect in your proximity sensors. My apologies for not showing that. Because in the particular exam, it is asked to you, okay, if you have a particular proximity sensor, let it be capacitive or inductive proximity sensor. Okay. When we spoke about the proximity sensor, let me open that particular this thing for 1 minute. Okay, so when we spoke about the inductive or capacitive type of proximity sensor, right, we said that this particular thing over here is an amplifier. Okay, so the question that is asked, if you have, now you have this type, now an amplifier, the moment you talk about an amplifier, immediately to your mind comes either a NPN type of transistor or a PNP type of transistor. Okay. A normal transistor can act as an amplifier. We don't need any great amplification circuits. A transistor can do that for you over here. So the question that is asked in the orals is, if you're having an NPN type of proximity sensor, so if this stage is having an NPN type of amplifier over here, it is obviously called an NPN type of proximity sensor. If you're having this in your circuit, say for example, your main engine flywheel circuit, and that one goes kaput, can you replace this with this or vice versa? In other words, if you're having a PNP, can you then replace a PNP with that NPN type of proximity sensor? Now, I will show you the video. 1 second, let me just give you an idea of what I drew. Okay, so this particular thing is your amplifier. Amplifier can be either NPN or PNP. And the question is asked, if your thing is an NPN and it's gone kaput, can you replace it with a PNP type of proximity sensor or vice versa? Okay, so I will show you this video, and after the video, I will ask you the question again, and if you can then give me the answer. Okay, I'm not going to show you the entire video, only the particular sections that are pertaining to the working. Okay. Okay, so this is an old man talking, so it takes some time.
Good morning, all. Today, we're going to look at how to test proximity sensors.
Okay, I'm just going a little ahead.
This is the PNP. Now,
Yeah, okay.
let me grab onto that. This one right here is the NPN. And it uses a pull-up resistor on the output.
Okay, so as you can see, an NPN transistor, and these two are the power lines, and this between this and this, of course, negative is taken as ground. Between 4 and 3 is your output, and as he said, he's using a pull-up resistor. Generally, it's about 10K or something like that. Pull-up, why? Is because it's taking the output and pulling it up to the voltage, the working voltage, whatever that working voltage. Remember, I said between 10 and 30 volts DC. Okay, so this is your NPN type of proximity sensor.
Proximity sensor, and it uses a pull-down resistor.
Okay, so here a PNP type, and instead of the resistor being connected to the positive, where it was called a pull-up because it is pulling it up to that particular voltage, here it is being pulled down to negative or ground. Okay, that is called a pull-down resistor. Okay.
On the output. Let me show that to you right there. If I can get up to it, that's it right there. That's
Okay,
the power
just forward
supply
it, and
with a
where
piece of
he is going to be
proximity
making the connections.
sensor to attach it to your machine. 10K ohm pull-up resistor. According to the diagram on the bag it came with, the brown wire is plus, that's VCC. The blue wire is ground, and the black wire is the output, the sensor output. Let me separate our wires so I don't short them out when I go to hook them up. I'm going to use 15 volts DC. The bag over there says you can use 10 to 30 volts DC as your supply. Okay, let's get those turned around there. Okay, the brown wire is plus. The blue wire is ground. Let me just output wire over here. Try to keep them separated. Okay. Let me get me a couple of hookup wires right here. I'm going to take this purple clip wire, connect it to our 10K ohm resistor. So that's going to bring the plus 15 down here into the proximity sensor to power it up. And then I'm also attaching that plus 15 to our pull-up resistor. The other side of the pull-up resistor, I'm going to connect to the output. So here's our plus 15 to the pull-up to the output. Let me get my meter into play here. Move those attaching nuts out of the way. And what we're going to do with our meter is we're going to look at the state change. Of the prox sensor when we flag it. The term flagging means we're activating the prox sensor. Get me another couple of clip leads here. Okay, I'm going to attach our meter to the output. I'm going to attach ground to power supply ground. We're using that power supply over there to make the plus and 15. We're going to attach that to the ground. Now we're ready. Just double check. Brown is VCC.
Okay, so note when this is the power supply, note when this LED comes on, the power supply is being given between 10 and 30 volts DC. I think it's about 15 or 16 volts that he provides. Note what is the reading on the meter, and then when he's going to bring a object to the, this is an inductor one, so he's going to bring a metal screwdriver. Okay, so just note the changes in this voltage. Okay.
Blue is ground and black is output. So we're ready to go.
Okay, so roughly 15.5 volts
15.54 volts DC on the output.
when he's first switched
of
it
the
on,
prox
and now
sensor.
when he's going to
That is
bring a
derived
metal
from our pull-up
object
resistor.
next to it in close proximity
These
of
prox
that sensor.
sensors that we have here
Then
are
notice
open
what is the voltage on the
collector.
meter.
So you have to have a pull-up resistor. Now let me flag that sensor and we'll see what happens. I'm going to use a metal screwdriver. Look at that. There's an LED
Okay,
in
so
here.
it's gone
And
almost
when
to
I flagged
0
the
volts.
sensor
Okay.
with the screwdriver, the metal of the screwdriver, the LED came on. Our state change, we went from 15 volts DC. Now we're at 0.774 volts DC. That's very close to ground.
So that's from logic 1 to a logic 0.
Remove
Okay.
the metal from the prox sensor and we go back up to 15.46.
Okay, so that's what happens for your NPN type of proximity sensor. Okay, so now let's see when he's going to do with the NPN. Sorry, that was NPN. Let's see when he does it with the PNP proximity sensor. Okay. So now that resistor is going to be reversed from a pull up to pull down by connecting it to the negative. Okay. That's all is the change for this type of proximity sensor. And then note when he switches on the same thing, same voltage, note what is the
plus
reading
voltage, VCC.
Okay, let's forward it a wee bit because it takes a lot of time.
As a pull down resistor.
Okay, now he's connected as a pull down.
This
In
to
other words,
ground.
he's going to connect it
This
to
is
the
our
black
meter.
one as he's
Connect our
doing now.
meter to ground. Connect the other side of our meter to the output so we can watch the state changes. Now, instead of the pull-up resistor going to plus VCC of the power supply, we're going to go to ground. Okay. Let's bring this out here so we can see it.
Okay, now he switched it on. Last time we were getting voltage, this time 0 volts. Okay. And now let's see when he brings that metal screwdriver here.
Look at this, we're at ground because of our pull down resistor. Let's flag it, see what happens. Ah, look at that. The LED also turns on in the proximity sensor. But we go from 0 volts up to 14.62 volts DC.
Okay, so you've seen an NPN proximity sensor where the voltage was showing first the moment he switched it on, and then when he brought a metal object next to it, the voltage dropped to 0. In the case of a PNP, when he put the proximity switch on, it went instead of going up to a voltage, it was showing 0 volts. And then when he brought a proximity, metal object in close proximity of that, then the voltage was showing. So now can anybody answer me the question is, can you use an NPN instead of a PNP proximity sensor, or vice versa in case one or the other fails? Anybody?
No, so we cannot use because the logic is changing from 0 to 1, 1 to 0.
Yes, absolutely correct. So the way to answer the examiner is, we cannot practically use the word practically, because we do not have the circuits to invert the output. If we had circuits such as NAND or a NOT gate or whatever, okay, we can change the output, isn't it? If you're going to get logic 1 by a NOT gate, we can just change the output and make it as a logic 1 and vice versa. But we don't have, no, even on board chip also to have resistors and all that as spares, we hardly find that on board. Okay, forget about resistors. These NAND gates are absolutely, any gates are not available as spares on board. Okay, so practically speaking, no, we cannot. But if we have all those circuits to invert the outputs, then yes, we can use. Okay, so be very careful when you're giving the answer to the examiner. Okay, right. So we saw that. My apologies, I had to stop in between as forgot to show it. So we have now understood how we can or cannot use a NPN. One second, let me get to the notes. Okay, so now we know that we can, or rather we cannot interchange an NPN with a PNP unless we have the particular thing for changing that particular output to the correct output. Okay. Right. So coming back to the thermocouple, we saw right at the beginning that the thermocouple is an active device that generates its own power, and that particular thing of generating its own power is because of the Seebeck effect. The Seebeck effect is nothing but having two particular different metals joined together at a particular junction, and when that junction is heated, you develop a voltage that is directly proportional to the heat developed at this junction. Okay, the output is generally in terms of nano or millivolts or microvolts. Okay, normally it is microvolts, as I said, max to max, some millivolts. Okay, right. What are the types of thermocouples that are available? Okay, we are seeing the most commonly used thermocouples on board, of which J and K are the most common ones. Okay, why I've highlighted this? Because you will definitely find J and K on board the ship. All the rest are very, very rare to be used on board the ship. There are further thermocouples that are using precious metals, okay, and give you very, very accurate temperatures. Okay, but since they are using precious metals, normally it is not used on board the ship. What are the types? E, J, K, T, and N. And please remember the ones that are highlighted because they have asked in the past what are the two different metals used. Okay, so let's take the E type. E type has chromel. No need of remembering what is within the brackets. Chromel consists of 10% aluminum, balance being chromium. That is going to be the positive leg. And the other metal is constantan, which is going to be the negative leg. Constantan is consisting of 45% of nickel, balance being copper. The J type thermocouple, the positive leg is iron and the negative leg is constantan. K type thermocouple has chromel as the positive leg and alumel being the negative leg. Alumel consisting of 5% of aluminium, balance being silicon. The N-type thermocouple has nicrosyl as the positive leg, nicrosyl consisting of 14% nickel, chromium 1.5%, balance being silicon. Nickel is the negative leg, nickel consisting of 4.5% of nickel, 1% of silicon, balance being your magnesium. Okay, so these are the types of thermocouple that we are using. Okay, we will discuss the cold junction compensation tomorrow, because that requires a bit of explanation and understanding with regard to what is cold junction compensation. Okay, so we will end our class here today and continue tomorrow. We should complete the temperature sensors, and then we'll move on to another set of sensors. Okay. So till now, any queries or doubts you have on any of the sensors we discussed? Okay then, gentlemen, we'll continue tomorrow. I'll meet you again 11 o'clock, and we will continue from where we left off today. So thank you very much for joining. Take care, and I'll see you tomorrow.